Thank you. All right. So thank you all for coming today. It's a pleasure to have Gabriel Menezes here with us today to talk about quadratic gravity. He's a he's a professor at the University of São Paulo. He did his PhD in CBPF, the Brazilian Center for Research in Physics, where I also did my master's, and we worked for some time in the same group. So it's particularly a pleasure for me to have him here with us. Um, he was already in any other very important institutes as the IFT in Brazil, the University of Massachusetts, and so on. And as I mentioned, now he's a professor in the University of São Paulo. And it's a pleasure to have you here to um, teach us a bit about quadratic gravity. Thank you very much, Gabriel, for accepting the invitation, and thank you all for coming.
Okay, Gabriel, thanks for the kind introduction, and also thank you for the kind invitation. And in return, I invite you all guys to explore a little bit of our work, which I'll try to summarize in this next hour. And I hope I can get some of you convinced that quadratic gravity is actually a quantum field theory that makes sense. So let's get started. So this is the basic outline. So holy cow, there's a lot of stuff that we can discuss. Of course, I cannot pass through all this with as much details that I would like. But I'm always open to discuss further any of the issues that you guys can find in the things that I will discuss here. But anyway, so let's start with the motivations, right? So why the heck I want to study quadratic gravity? So besides the fact that if you consider a quantum field propagating on a curved background, if you want to renormalize the theory, you are forced to consider curvature squared contributions in the gravitational action. You can also take as a motivation the standard model, right? The standard model of particle physics is the theory that we best know that describes the particle fundamental interactions that we have current access in experimental settings. And this standard model is a renormalized quantum field theory. So in order to construct this theory, many extra ingredients were needed, and they needed to be understood as well, such as asymptotic freedom, spontaneous symmetry breaking, new-Abelian interactions. So if you want to use quantum field theory to describe the quantum interactions of the gravitational field, you also need extra ingredients to be understood. So in particular, these extra ingredients are associated with the fact that if you have R-squared terms in your fundamental action, propagators, the metric propagators are going to be quartic in the moment. So these extra ingredients here that I mean is related to the presence of quartic propagators. So the fact that you have quartic propagators, as we see a little bit here, comes with a lot of unusual features, unusual in terms of what you think is usual for a quantum field theory. So we have to understand if these unusual features completely dismiss this theory, so if it generates inconsistencies, or if it generates unusual things that you can put up with. So what is this theory that I'm talking about? This theory is given by this action, right? And I list some of these current authors and explorers here, and I'm sorry if I forget some of your names, sorry, because it's a lot of people that I have to remember, but anyway. So this is the action. So this is our starting point. So you see the part that is the usual Einstein-Hilbert stuff, right? And then the curvature square parts, right? This is actually the Weyl tensor square plus surface terms. So the good news is that this theory is renormalizable. And the reason is that the propagators fall as 1 over q to the fourth in the UV. So this means that your high energy divergences are turning into renormalizable ones. You can see this using power counting. When you use power counting, you will find that the most divergent vertices in the UV are given by these guys. But these coupling constants are dimensionless. So this theory is power counting renormalizable. And it can also be asymptotically free. I will give a few words on this because recently we have recalculated the beta functions associated with these couplings here. But there is no free lunch and there are bad news. If you take the spectral representation of propagators, as Chalin and Lemon has beautifully taught us decades ago, you will learn that propagators cannot fall faster than 1 over q squared for large q squared. But here you have this fall, right? So some of our cutest ingredients must not be there after all, but which or each ones, right? Unitarity, causality, positive norm states, Lorentz invariance. Which of these ingredients are not here anymore or are here in terms of an emergent feature, right? So you can see this by looking at the propagators of the theory. So usually you write the propagators in this term, but you can also use partial fraction decomposition to write it in this terms. In this term, the minus sign here is the guy that is responsible at high energies to have this behavior here. But it's also the guy that gives you the problematic issues here. So the first problematic issue that we can discuss is one that is known almost more than 100 years ago, actually, which goes by the name of Ostrogatsky's instabilities. So what is this? So this is a theorem that is 150 years old by Ostrogatsky that is related to what happens to theories that have higher derivative terms, especially higher derivative time derivatives terms, and then you want to go to the Hamiltonian formulas. So let's proceed similarly to what he did. So you introduce two canonical momenta, and then you take the Lagrangian, which is typically you can choose a Lagrangian such as this. The chi field is a normal field. And every time that I say a normal field is just a field that has two derivatives, right? So if you do the typical calculations, the Legendre transformation to calculate the Hamiltonian in his Ostrogatsky construction, you find this linear term in the canonical momentum pi 1. So since this guy can come with any sign, this means that this can be as negative as you want. So the Hamiltonian constructed in this way is not bounded from below. So this is the famous classical Ostrogatsky instabilities. So his construction was meant to reproduce Hamilton's equations, or to put in another word, you want the Hamilton's equations to reproduce the Euler-Lagrangian. So this is his construction. But this is not actually a unique choice. Indeed, this is not the choice that you do in quantum theory. The fact that you construct a Hamiltonian in quantum theory is associated with the fact that you want to identify energy eigenstates. Think, for instance, the traditional harmonic oscillator. You use this to identify not only which are the high energy eigenstates, but to have positive energy eigenstates, which we call quanta. So this is the focus on the quantum theory, not to actually reproduce the Hamiltonian equations. Of course, in normal quantum field theories, uh, this comes with the equivalence between different quantization prescriptions, right? But in these theories, in these higher derivative theories, you are not guaranteed that different quantization prescriptions will give you the same outcomes. So let's see, for instance, with this model here, and try to quantize it using path integrals. So this is just a toy model. So let's first eliminate the high derivative term. You can use a kind of a inverse Huber-Stratonovich transformation, and then you by introducing an auxiliary field, and then you define a new field, right? In such a way that your Lagrangian can be written in this way. So you have a part that is describing a normal field coupled to another normal field, and then you have a funny field, which is also coupled to the same high normal field. They don't have interaction between them. So this means that path integral factorizes, right? So you have this usual path integral given by this action here, and you have this funny path integral with this extra minus sign here. The fact that you have this minus extra sign here signals that once you calculate the propagator, the I epsilon prescription comes with an opposite sign. So since this theory has these path integrals factorized, you can easily integrate this guy. So let's integrate this field, this funny field, which I'm going to call a ghost field because it's not a normal field. So what you get is this expression, right? With this funny looking Feynman propagator with two unusual minus signs, right? So you have a minus sign here, as I told you, and I'm using the mostly minus metric convention. So usually you would expect a plus I epsilon here, but you also have a minus sign here. So you have two unusual minus signs, which will be important for us in what follows. So this theory, if you look at the low energy limit, which means taking the mass, which was this mass parameter here, much larger than the energies. So the propagator is just a delta function. This will turn into a shift in the hypothetical quartic interactions in the coupling of the sky field. But it's suppressed by 1 over m squared. So even though it comes with a minus sign, it's not big enough to destabilize the chi field. So, of course, this is in accordance with the Apple-Quiz-Pearson theorem. So this is implying that this field at low energies decouples from the theorem. And the low energy Lagrangian just contains the H and the chi field, which are normal fields, right? So actually, if you want to analyze the classical limit of this theory, the classical limit actually is normal, right? The classical limit is not just taking the H bar and putting it into zero, right? The best way for you to do this is to analyze a kinematic region in which quantum effects are not important. And this is associated with long wavelengths, longer than the, let's say, the Compton wavelength associated with the chi field, low energy limits. So once you go to this limit, the theory is completely normal. We don't have this this problem associated with this ghost field. So it completely behaves normally, right? So at least for some theories, this is just a toy model. It seems that you can avoid at the quantum level the ostrographic instabilities, right? Another common misconception that comes with this kind of theories, especially quadratic gravity, concerns the spectrum. And this is related to a common law that the massive ghost carries negative energy. So, of course, if you start with a classical analysis, this seems to show this because you can go back here and then you can see that you have this overall minus sign, and then you could interpret this minus sign as giving you a negative Lagrangian. So this would generate a negative Hamiltonian, and this would generate a negative energy ghost. But let's see how this is not actually correct, or at least this doesn't give you a useful interpretation, right? So the first thing you have to do is to calculate the propagator theory. So this is a typical calculation of the one loop propagator with one loop corrections in quadratic gravity. So you have this guys here. This comes from the R-square terms. This is the usual Einstein-Hilbert term, and these are loop corrections. This n here is associated with possible low energy modes that are coupled to gravity. Okay, so this propagator, you can write it in a compact form in this way, right? Without these extra tensor ingredients, which are not actually important in our analysis, right? So this propagator has two types of excitations. The first one is the pole is given by the pole at q squared equals 0. So this is the stable particle of the theory. In terms of the quadratic gravity, this is just the usual gravity. But however, you also have a massive excitation, which at one loop order, which the self-energy has this form, comes with an imaginary part. So this is actually a resonance, right? So again, you have these two unusual minus signs here. So the first question will be like, okay, if it's a ghost resonance, how do you know it's created? So you can envisage a simple experiment where you scatter matter particles, normal matter particles, coupled to gravity at high energies, where these heavy resonance is produced and then it decays. So this simple example shows that if these guys here in the initial and the final states are normal particles, then they carry positive energy. So there is no way that if you have initial particles with positive energy and final particles with positive energy, that this resonance also carries negative. This resonance carries negative energy. There's no way. They have to be also carrying positive energy. Right? Okay, so even it carries positive energy, you have this minus signs here. So it qualifies as a ghost. So some issue must be related to it, right? So uh, uh, one possible issue is associated with stability, right? Because you can, in the weak coupling limit, Fourier transform this propagator and find that you have exponentially growing modes. So a typical Fourier transform at the weak coupling limit of this propagator actually will give you this form here. So actually, the exponential is a decaying exponential, not exponentially growing exponential. So these guys here are the poles associated with the stable particle, the normal particle, and these funny looking poles are the poles associated with the ghost. So you see this extra part here in the propagator is associated with a backwards in time propagation, right? But with positive energy. And this backwards in time propagation of positive energy is supported not only by looking at the path integral with this minus signs here, but also if you calculate the retarded propagator. If you calculate the retarded propagator, you see that you have these funny poles in here, right? Sorry, these funny poles in here that gives you an unusual term where where usual retarded propagator wouldn't have, right? So we come up with a cute name for this ghost modes, which we call the Merlin modes, right? So actually, we say that this ghost modes, right? The ghost is not actually a ghost, but it's actually a wizard, right? So okay, so it seems that you don't have issues with positive energy. These ghost modes carry positive energy. It seems that the theory is stable. I'm not giving, of course, I'm not giving a complete proof of stability, but I'm giving hints that it could be stable. So where is actually the problem? So the problem seems to be causal, right? And it's connected exactly with the fact that you have this funny minus signs, not only in the I epsilon, but in the overall propagator. And this is connected with the fact that uh, in the path integral quantization, instead of having e to the plus is, you have e to the minus is, right? So if you let's so before we understand this violation of causality, let's consider a field theory where instead of considering the usual path integral, you are considering a path integral with a minus. In terms of time reversal symmetry, this makes sense, right? Because time reversal operation is anti-unitary. So if you want to do a time reversal operation in the path integral, you have to change the plus sign in the exponential, right? In the argument of the exponential. So actually, you have this kind of two, 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 two possible ways to quantize your field theory, right? It's by now it's just a normal field. It's not a higher derivative theory. So it's just a normal theory in which I just change the sign of the path integral, the argument of the path integral. So this will give you two different uh, propagators. And these two different signs here are associated with the fact that you have two different time directions in which causal process occur. This we come up with a name to distinguish this, which we call the error of causality. Basically, the error of causality distinguishes the past light cone from the future light cone. And what is what is important here is that the measurement of time is completely a conventional stuff, right? You can measure time. You can measure time by paralleling this to your causal direction. So you count 1, 2, 3, 4, 5, the forward direction. But you can do the opposite as well. You can take, for instance, an hourglass, right? You can take, you can count times as this chamber is being filled or as this chamber is being empty, right? So this also has some connection with the error of time, which I will not have time to discuss with this, but I'm happy to discuss further if you guys are interested on that. But the idea here is that you have an error of causality associated with these I epsilons here in quantum field theory. So this is not something that we have invented. So this is just something that we have identified. And this is associated with the fact that the measure of time is just the way you measure of time is a convention, right? But causal reactions in particle physics only goes one way. So, okay, so this is the most useful way to identify the violation of causality that I mentioned just for you. Because in this type of theories that we are analyzing, high derivative theories, actually, you have something that you can call dwelling errors of causality. Because you have two modes with different I epsilon prescriptions. So you have mixing conventions. So here, for instance, you would have a convention that would go as we would associate with plus I epsilon. And then this guy here, because you have a I to the minus IS in the path integral, this guy here would come to the an opposite I epsilon prescription. So you have an opposite error of causality in comparison to this guy. So at the energies, at the energy scales, in which those two guys are important, you cannot distinguish an overall error of causality. So this means that you have violations of causality. But of course, you can ask yourself, okay, but is this valid to all energy scales? So of course not. So if you consider low energy scales, right, in which this guy is much bigger than this guy, so you can Taylor expand this guy here, right? And then go to low energies, let's say. There is just one error of causality given by this stable modes here. So in the end, even though you have dwelling errors of causality, the stable modes determine the error of causality at low energies. So put in other words, causality, as we know in these theories, is an emergent feature. So at energies compared to the mass of the ghost mode, you have violations of causality because you have dwelling errors of causality, and then you cannot distinguish a preferred error. But once you go to the low energy sector of your theory, and you only have normal propagators, the stable particles will determine the error of causality. So it's important for this ghost mode to decouple from the theory to understand how you can recover causality as we understand. Of course, if you think of general high derivative theories, you can think that this is a crazy feature to put up with, right? But maybe this is not as crazy once you go to gravity, right? Because this happens for gravity, this happens at the Planck scale, because this mass for the ghost, in the spin to ghost in quadratic gravity is proportional to the Planck scale. It's roughly at the Planck scale. So it would be not so crazy to think that at the Planck scale, you have a sort of an indefinite causal structure, right? So actually, right, all gravitational theories must display some sort of causal certainty due to space-time fluctuations. You can see this even at low energies in an effective field theory calculations. This is an effective field theory calculation. This is a theory where you study light bending, the leading quantum corrections to light bending. So you find at one loop that there is this term which depends on the particle species. S is the spin of the particle. So this is not a universal correction. So usually you take the trajectory of massless particles to define light cones. But once you have this non-universal correction, you see that a light cone is not a useful concept in quantum gravity. Right? So it might not be so crazy to understand these violations of causality in quantum gravity. So here you have a theory that gives you this, right? I will not have time to 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 discuss a little bit the 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 consequences associated with quadratic gravity, but the fact the fact that you have this funny looking poles means that your uh, your propagator in the complex space or in the complex momentum space might have no analytic feature. And this is related with the fact that you have these violations of causality. So this explains why the lemma representation doesn't work here, right? So in fact, here, uh, using the Schwarz reflection principle, you not only have this complex pole, but you also have to have a complex conjugate pole. And because quantum corrections will introduce this law, which introduces a branch cut, you have three pole-like structures. So actually, you can have a lemma representation, but it's sort of a modified lemma representation. So you take this propagator, use the Cauchy formula with this contour here. So these are the complex conjugate poles that I was mentioning. And this is the branch cut associated with the quantum corrections. So this is not something that we did. Actually, it goes back to some Hedis lectures by Coleman. So he was the first to identify this structure, right? But the essential point here is the fact that even though you have this three-pole-like structure in your propagator in this modified lemma representation, you can prove that those two guys here, right, cancel the pole-like structure from each other. So actually, you only have this guy here. In the narrow width approximation, this cancellation is perfect, is exact. So you actually only have this guy here. But it's important to keep this guy here to see how things come about, to see uh, uh, how this ghost mode is actually an unstable particle. A fun unstable particle, but it's an unstable particle. But the fact that it is an unstable particle means that unitarity is preserved here. This is also a common law in this kind of theories that unitarity is not preserved. Actually, it is preserved. And in some ways, the proof of this, the proof that the theory is unitary goes along the same lines that Veltman did back in the 60s to prove that a theory with unstable particles is actually unitary. You just have to consider here in these unitary sums only stable particles, only particles that appear in the asymptotic spectrum. So this means that also you construct the generalized optical theory, which is this equation. Using the cutting rules, you only cut internal propagators that are associated with stable particles, right? There is a corollary to that, which is associated with narrow width approximation. In this case, off-shell production is not as relevant as the resonance production. So in this case, you can cut lines of unstable particles. This will give you the same result as cutting lines of the decay products in terms of only stable particles. So you can mimic this context, this reasoning for the ghost resonances that appear in this higher derivative theory. So unfortunately, I will not be able to give you a full proof in this talk because it's a really dense proof with a lot of techniques, right? But the takeaway message is that once you remember that the energy flow of this ghost modes go backwards in time, right? The positive energy flow, once you take care of this, you can use the same technique as Veltman to prove that these theories are unitary because these ghost resonance decouple from the spectrum. But there is a catch. As I told you in the beginning, there is no free lunch. The corollary here, the narrow width approximation, comes with a catch that you cannot use the usual final contour. You have to use a funny contour that goes by the name of a Liouville contour. At one look, you know that this is okay. You also have to, if you want to calculate one loop amplitudes, you also have to use another prescription together with the Liouville contour. Something that we don't know, or actually no one knows, if this whether this contour, this prescription works at high orders in perturbation theory. So this is something that no one knows, but at least at one look, and using the narrow width approximation, you have to use the Liouville contour. So, okay, so another thing that I would like to discuss with you guys that I mentioned before in the beginning is associated with the calculations of beta functions, right? So what's the idea? So beta functions are associated with something that we call the running couplings. And running couplings are useful in order to understand when you can use an amplitude, how you can use an amplitude which you renormalize at a given energy scale, and you want to use this amplitude at a very much higher energy scale, and you want to eliminate the large logs that typically your amplitude will carry. So an useful concept is running couplings, right? In renormalization group equations. But one thing, once you calculate amplitudes, that you have to be careful is to identify which are the terms that really have external momentum dependence, because these are the terms that once you go to high energies, they will give you these large logs. To put in simple words, there are some diagrams in your Feynman diagram expansion that will not carry momentum dependence, external momentum dependence. So typically these guys in the renormalization of amplitudes will not contribute to these high energy logs, right? Typically, these are tadpoles. So in principle, once you calculate these running couplings, you don't need to consider these tadpoles, right? So for normal theories, two derivative theories, this is not an issue. But for theories that carry a mass scale, such as these higher derivative theories that we were discussing, there could be issues associated with the presence of tadpoles. So you have to identify the tadpoles and eliminate them from your calculation of these running couplings. So we did this for quadratic gravity. So this is the theory. So you can proceed as usual. You can linearize the action, choose a suitable gauge fixing, of course, considering for the help of ghosts. And then in the end, you have this form of the operator, of the differential operator acting on the gravitational field, on the graviton fields. Right? So those guys here depends on the background curvature. So you can usually what you do, you use heat kernel approaches, right, to calculate the beta functions. Heat kernel approaches successfully give you the UV divergences. And the common law is once you calculate the one loop UV divergences, the coefficient gives you the beta functions, right? So the first issue is that in this calculation, there are tadpoles. But we don't want to consider tadpoles here because, as I mentioned, tadpoles do not depend on external momentum. So they will not contribute in the calculation of the amplitudes to the, the large logs, which will depend on momentum. So the first thing is to try to eliminate the tadpoles here. But then, technically speaking, you use the same as we did actually. You don't need to do this, but this is how we did. You use the original U-turning approach, use the background itself a small deformation of flat space. So actually, the operator that you consider is here. So each of these terms is an infinite series of f. So actually, you are interested in the 3-point couplings with two f's and one h, right? So the first problem that appears here. If you just eliminate the tadpoles, the final expression that you obtain is not a covariant expression, right? So for some reason, this has stopped here.
We can still see your screen.
Okay. Can you see the slides now?
Yes.
Okay. Okay. So the first issue is that if you just eliminate the tadpoles from your calculation, the final answer is not going to be covariant. Covariant, what I mean by covariant? Your final answer is going to be written in terms of an expansion of the H field, which is your external field. And then you have to identify in the expansion as an expansion of these covariant guys here, right? And then you cannot manage to identify with the logs, of course. So you have the C log box C and R log box R. These are the covariant expressions which I mean. So if you expand this, you have to find the same expansion in terms of H. So if you just eliminate the tadpoles, you find that the final expression cannot be expressed in terms of C log box C or R log box R. So this is not a covariant expression. So this means that you are missing some contributions. One contribution that you are missing is the U. U do not give you UV divergences. So you don't need to consider bubbles constitute of only U's in principle. But they give you infrared divergences. The infrared divergences, they appear not because we are probing the low energy limit, but because a bubble diagram composed of only quartic propagators is pretty much like a box integral with 4 propagators in which you collapse 2 of its propagators. And a box integral does not have UV divergences. It only has infrared divergences. But these infrared divergences come with logs, and these logs contribute to the beta function. And also, you consider those guys, you can prove that your final answer is covariant. So these are the extra ingredients that you also have to consider. So these are the flow lines of the beta function. So these are the new beta functions that we calculate. And then you can identify 3 lines or separatrices that mark the boundary between different behaviors of the beta function. So you have this line here, lambda equals 0. So you have this line here, and you have this line here. If you want to study asymptotic freedom, you have to search for the region which is attracted towards the free field fixed points. So this is this region. But then you have an issue concerning the size of these guys here. In order to not generate tachyons, you have to fix the signs here. So the absence of tachyons tells you that you have to be here in this region. But the asymptotic freedom region and the absence of tachyon region overlaps in this part. So you have a specific trajectory which gives you asymptotic freedom for both copies. This is different from the usual calculation in literature. The usual calculation in literature tells you that the only way that you can have both copies to be asymptotically free is to have the psi to be positive, which means that you have a scalar tachyon. So in our new calculation, we prove that you can also have asymptotic freedom in the absence of tachyons. So this is great, right? So this is telling you that possibly quadratic gravity has asymptotic behavior pretty much like QCD. Of course, this is a bold statement, right? In order to check whether quadratic gravity amplitudes have good UV behavior, you have to actually calculate loop amplitudes. And this is a completely different enterprise, right? So, because on one hand, loop amplitudes are difficult to calculate. And on the other hand, gravity amplitudes are notoriously difficult to calculate. So the best course of action here is to use modern approaches, right? One modern technique that you can use is something that we call generalized unitarity. Generalized unitarity uses the fact that the theory is unitary. And then you can use unitary sums and in order to build loop amplitudes. The basic idea is to construct higher loop amplitudes from lower loop amplitudes. So if you want to calculate, for instance, a one loop amplitude, the basic ingredient will be given by three-level amplitudes. So it's a way to glue, a way to construct loop amplitudes by gluing lower loop level amplitudes, right? So we'll not have time to discuss fully the method, but the idea is the following. Take a basis of mastery integrals where you can expand your loop integral. At one loop, we know this basis. So for instance, in 4 dimensions, all one loop amplitudes can be expressed in terms of scalar boxes, scalar triangles, scalar bubbles, possible tadpoles, and possible rational terms. So this is just an expansion in terms of a basis of mastery integrals. So how you calculate these coefficients, the unitarity method tells you how to calculate. And the basic thing is that instead of cutting just 2 internal lines, which is usually the textbooks in quantum field theory will tell you, you will cut more internal lines. So you can cut 3 lines, you can cut 4 lines. At 4 dimensions, at one loop, the most number of internal lines that you can cut is 4. And by cutting internal lines of your amplitude, you will find a result that is just a multiplication of 3-level amplitudes. And this multiplication of 3-level amplitudes will roughly allow you to calculate these coefficients. So this is quite a quick summary of the method, right? But this is not enough, right? Because it's enough to calculate loop amplitudes to any theory. But we're not talking about any theory. You're talking about gravity theory. So you also need an extra ingredient that goes by the name of color kinematics and double copy relations. So double copy relations is just an expression for this slogan, gravity equals gauge theory squared, which some of you guys might have heard, right? So how does this work? So actually, you start from a generic Young-Mills theory of only cubic interactions, right? So we have a propagator, you have a kinematic numerator, which is just a Lorentz invariant product, scalar product of external polarization, external momentum, etc. And you have color factors due to the fact that you're working with a non-abelian theory, right? So these guys here are associated with Feynman diagrams. Feynman diagrams by themselves are not gauge invariant. The amplitude, the on-shell amplitude, is gauge invariant. So this means that those numerators are in general not gauge invariant. So you can always deform this, you got these guys here, and the amplitude will stay the same. So you can prove that if you take these numerators and correctly deform those guys here, uh, using the Jacobi relations that these color factors will obey, the amplitude is invariant. So you can use this to build up a representation for these numerators in which they obey the same algebraic relations of the color factors. So you call this the color kinematics law. So this is Yang-Mills theory. So what does it have to do with gravity? So here's where magic happens. Take a Yang-Mills theory where you use this representation where the numerators obey this, and then replace the color factors by these numerators, and then boom, you have a gravity amplitude. The thing is even more magical because you don't need to consider two numerators that obey color kinematics duality. You can consider two different Yang-Mills theories in which one of them obeys color kinematics duality and the other is given by the representation that not necessarily obey the color kinematics duality, but the amplitude that you're going to obtain using this double copy prescription is still a gravity amplitude. Of course, this is just words. You have to prove this. In actual level, you can prove explicitly this. One way to prove this is to prove that this theory, that this amplitude here, can be recast in terms of color order amplitudes of gauge theory, and this is the usual KLT relations, Kawhi-Leland tie relations that come from string theory. So this is one way to prove. Another way to prove is to use recursion relations and prove that explicit calculations give you gravity amplitudes as given in this prescription. So,
Gabriel,
yeah.
just to let you know, so I'm giving a bit more time because we started a bit later since the
Yeah,
process is beginning, but we have 5 more minutes.
5 more minutes. Okay, thanks.
Or,
So you have two great ingredients, right? You have generalized unitarity, where you can use to calculate loop amplitudes, and then you also have double copy prescription, where you can actually calculate gravity amplitudes, right? So this is an example of how you calculate using the spinor helicity formulas GR amplitudes, right? Starting from Yang-Mills amplitudes. You have to be careful with this because you have a caveat, because in 4 dimensions, Yang-Mills theory has 2 degrees of freedom associated with the two different helicities of the blue. So as far as I know, 2 times 2 equals 4, right? But graviton has only 2 degrees of freedom. So you have 2 extra degrees of freedom, which are just the dilaton and the Cobb-Ramon form field. In the string theory perspective, this is expected. But if you want to just do a pure gravity calculation, you have to get rid of these events. It's not so difficult to calculate, to eliminate these guys. You have to use state projectors, or if you are in 4 dimensions, you can just correlate adequately the helicities of the gluons, so you can have only graviton amplitudes. This is possible to do, but you have to take care of this. So moving on to the higher derivative theories, right? Can we do a similar stuff for higher derivative theories? The partial answer is yes, right? The partial, I mean partial because we know up to 3 and 4 points and an actual level. Higher points, higher amplitudes of higher multiplicity, we still don't know the answer. But it seems that the double copy story can be reproduced as well here. So for the Young-Mills side, you started with a higher derivative Young-Mills. So this is the higher derivative Young-Mills that you start with. So you can calculate the amplitudes here, right? I'm passing this because this is too technical. I don't have time to this. And then you have to check for the color kinematics duality. You prove that this series has this color kinematics duality. This is an amplitude, for instance, is an example involving massive scalars and tremulins here. This is a tremulus represented by this bold notation. And really doesn't matter what these notations are here, but these are massive spinors, which is a massive generalization of helicity spinors. But you can prove that these guys here, these numerators, obey color kinematics duality. So if they obey color kinematics duality, you can construct the higher derivative corresponding gravity amplitudes using BC8 double-copy. So this is not actually, I call it quadratic gravity amplitudes, but it's more correct to call the Einstein-Weyl theory because we don't have the rich scalar square in here, right? So you can use this map, which is a double copy map, to construct the tree-level amplitudes in this theory, at least up to 4 points, right? So I'm passing through this here, but I'll be happy to discuss further those amplitudes, but you can prove this, right? So these are examples of how you calculate this amplitude, which would be a really messy calculation if you're willing to use standard approaches, right? And then you can also calculate a one loop amplitude associated with this process here, right? And run. Using not only the double copy approach, but also the generalizing type of thing. I'm going to skip this, but this is also associated with all those modern methods, and you can also use this calculator. I'm going to also skip this, but this is a beautiful application of all those methods in double field theory. Double field theory is a quantum field theory where you can introduce the T-duality symmetry of string theory. So you double the coordinates in order to use this. So you can prove that at least up to quadratic order, the double copy at the level of the action of a higher derivative Young-Mills theory reproduces, in a certain sense, the quadratic terms coming from the Weyl tensor square action. So this is the takeaway message that we did here, right? But I won't have time to go through this in details. Well, so this is something that we are actually doing right now because we didn't talk about phenomenology, right? I was just talking about the structure of the theory. So, but one important consequence from our beta function calculation is the fact that every time that this guy is important, this guy will also be important, right? So this will obviously have some consequences in inflation. So one possible way is that the fact that you have a causal interactions that spread effects outside the usual outcome, one possible consequence is that using only quadratic gravity, typical inflationary phase might not be needed. This is, of course, a bold statement. We are not, of course, uh, uh, ready to actually argue that, because it might not be this fact. It might be that this homogeneity generated by the causal physics will provide the uniformity required for the start of inflation. So you still have an inflationary phase. So this is an ongoing work, but it's a typical application of all those things that I was discussing. So I will leave you with some other cool stuff that I've been doing in other near future perspectives, especially associated with this calculation of amplitudes in higher derivative theories. And then I'll stop here and I'm ready to take questions. Thank you, guys.
Thank you very much.